in order to do the calculation of how we get to beats, we're going to make a few simplifying assumptions. Now, these aren't necessarily required to have beats appear, but just for the sake of our math, they're going to help it. So the first is that we're going to assume that the waves have the same amplitude. This isn't entirely required, but to have them go as quiet as possible in the beat does require that they have the same amplitude. If they have slightly different amplitudes, then you're going from louder to less loud, not all the way to quiet or momentarily silent. We're going to be using a position of x equals 0. This doesn't really matter. We just need some position to think about what the amplitude there is, what's happening in time. And we might as well use x equals 0, so it simplifies the math. We're going to assume that our sources are in phase. Now, again, when I say this, I mean that the phase constant in the equation is the same, because they don't stay perfectly in overall phase because they have different frequencies. Lastly, we are going to use an initial phase of pi. We said that they have the same phase, we're going to call it pi. The reason for this is because omega t has a minus sign in front of it, so once we add pi, that makes it positive. So this is a little subtle in that this isn't required, but it means that we don't have to carry around this minus sign. So this is what we're starting with. We're adding two waves together that have the same amplitude and have different frequencies. And we're starting off calling it just this angular frequency omega, but we can convert to regular frequency f later at the end. And again, normally there would be a minus sign there, but by putting in a phase of pi, that makes it positive. So to get from here to something useful, we use this trig identity, which has come up before. So by using this trig identity, we now get to have a cosine function multiplied by a sine function. So the reason that this is interesting is you notice that now we have two functions that both depend on time. So our overall amplitude now is 2a, but then we have this function which depends on our phase difference, and then this function that depends on our phase sum. Now this phase sum is divided by 2, so we can actually call this average angular frequency. And so the reason for that is, again, we have a sum and it's divided by 2. Here we have that difference between angular frequency. I think I said phase earlier, didn't I? That was a mistake. This is angular frequency. And so we have a difference divided by 2. So this isn't the average. This is something else. And in general, when we talk about beats, we're talking about two frequencies that are really, really close together. So this number isn't 0, but typically this is going to be a very small number, which means that this frequency, this beat frequency that we're about to talk about, is actually pretty slow. So for instance, 1 or 2 per second. So we can rewrite that first term as a modulation frequency. And again, that was the difference between our two, technically divided by 2. So that's going to be our modulation frequency. And then we had the average frequency. So the average frequency is giving us all this fast stuff up and down. So the average frequency is really, really fast. This modulation frequency is the one that's much slower. So this is important to recognize, that we have two different frequencies occurring here. And you can think of this, for instance, as there clearly being a pitch, there clearly being a note. So for instance, maybe this sounds like the middle C on a piano that's getting louder and quieter. Well, the middle C on the piano has a frequency of, say, a few hundred hertz, but typically this beat, the modulation frequency or the beat frequency that we hear is maybe happening 1 or 2 times a second. Now the other thing to recognize is that while we do have this frequency that you would pull out from this long wavelength here, that would be what our beat frequency is, but that's actually twice the modulation frequency. So if you just listen between soft and loud, that takes this amount of time. But if you were to trace out the full sine wave, that takes this amount. So that's why there's the factor of 2 between the modulation frequency and your beat frequency. And again, we can think of that as being given just by the difference between the two frequencies originally played by our two sources. So again, mathematically what's happening here is they're going in and out of phase, and the frequency at which they're going in and out of phase is given by their difference of their frequencies. So make sure you understand, again, why there's two different frequencies here. Again, the frequency that's being modulated, and then the frequency at which the modulation is occurring. So again, a lot of terminology to deal with here, but when we do a demo of this in class, I think it'll be much more clear to you what's going on.